Hello friends, welcome to this third video on analytic function. This video will concentrate on the construction of analytic functions using the Milne Thomson method. Before moving on, we will try to recollect what is meant by analytic function. A complex function f of z is said to be analytic if its derivative exists at any one particular point as well as in the neighborhood of that particular point. So basically, if the complex function has its derivative to exist, then the function becomes analytic. The point at which the function is not analytic is called as a singular point. There are going to be two conditions that has to be satisfied to make sure that the function is going to be analytic at that particular point. What are they? The first condition is that the partial derivatives must exist. The second condition is that the CR equations have to be true, namely ux is equal to vy and uy equal to minus vx. Having these things as base, which we have already seen in our video 1 and 2, we will now try to construct an analytic function using Milne Thomson method. So what is this Milne Thomson method? So say suppose we have been given the real part u and we will have to find the analytic function f of z. So the idea is to find or construct the analytic function f of z either if we have been given with the real part or with an imaginary part. We know that f of z, a function of z, can be expressed as u of x comma y plus I v of x comma y. So if this u is given, how can I construct my function f of z? Or if this v has been given, how to construct my function f of z? So this is going to be the prime motive of Milne Thomson method. So now we will see how to apply it. F of z is u of x comma y plus I v of x comma y. Let me try to find the derivative. Since this is two variables involved, I can go for the partial derivative with respect to x. So I will have ux, u when I differentiate with respect to x, I will have it as ux. V when I differentiate with respect to x, I will have vx. But what is available for me? I have just u which is available for me. So I know that if it is going to be analytic in nature, the CR equations have to be true. What are the CR equations? Ux is equal to Vy and Uy equal to minus Vx. Since I have only u which has been given to me, the variable v with respect to x is now replaced with the term of u. So what is my Vx? From over here, I have my Vx to be equal to minus Uy. So this I replace it, giving me the derivative f dash of z as ux minus I times of uy. Primarily, the Milne Thomson method can be solved in 4 steps. So what are they? Step 1. Find what is your ux and uy from your given function f of u comma v. Step 2. What we need is going to be ux and what we need is going to be my uy. This ux, I assume it to be a function phi 1 of z comma 0. So, u with respect to x comma y, I differentiate with respect to x and then name it as phi 1 of z comma 0. So, practically what I am doing is wherever I have x, I replace with this z and wherever I have y, I replace it with 0. So, I replace x with z and y with 0 in the derivative which we have obtained in the step 1 and name them as phi 1 of z comma 0 and the second derivative u with respect to y as phi 2 of z comma 0. Go put it back in your f dash of z. So that is my step 3. So what is my f dash of z? Ux. What is my ux? Phi 1 of z comma 0. Uy minus I times what is my uy? It is phi 2 of z comma 0. Step 4. From my f dash of z, how to find your f of z? I will have to integrate the answer. So whatever answer I get in my step 3, integrate it with respect to dz. Because now instead of the two variable x and y, I have now converted into a single variable called as z. So carry out the integration with respect to z. This will give me my analytic function f of z, and we are done. This is the case when u is given. Now, what is the case when v is given? The same process can be carried out with respect to v. What is our CR equation? Ux is equal to Vy and Uy equal to minus Vx. Instead of differentiating with respect to x, what do I do is, I now replace the values of u in terms of v because v is the value known to me. So what will my ux be replaced as? Ux will be replaced as Py. And what is this Vx? Px is already a variable in V, so I retain it as such. So I have f dash of z to be equal to Vy plus Ivx. Notice very cautiously, the first term is with respect to y. The second term is with respect to x. Normally, we have the tendency to first differentiate with respect to x and then with respect to y. But when it is coming for given value of v, we do it in the opposite way round. So the first derivative is computed with respect to y and the second derivative is computed with respect to x. So I compute the partial derivative in my step 1. In my step 2, I assume v with respect to y, that is my first quantity which I have computed as phi 1, and v with respect to x, the second thing which we have computed as your phi 2. So now the same way replace x with z, y with 0, and after resubstituting this, make them as phi 1 and phi 2 and put it back in your f dash of z. That is your step 3. So I have phi 1 of z comma 0 plus I phi 2 of z comma 0. Step 4. From your f dash of z, how to get your f of z? Just integrate it with respect to the variable z. So that will give me my final answer. So this is how you construct the analytic function f of z, either if you have been given with the real part u or with the imaginary part v. So having known or now followed up with the steps, we will try to apply it to a problem and see. Problem number 1. What we are going to do is, given the real part of the analytic function u, which is equal to half log of x square plus y square, find the analytic function f of z. So I need to construct my f of z. I have been given with what? The real part u. So this now is going to be my first step. Okay, what is going to be your step 1? Compute ux and uy from the given u of x comma y. So let me do this. So what I am going to do over here, I am going to compute my ux and uy. So u with respect to x is going to be half. What is going to be differentiation of log x? That is nothing but 1 by x. So differentiation of log x square plus y square is 1 divided by x square plus y square. Now the inner function has to be differentiated with respect to x. What is going to be x square with respect to x? I have it as 2x. What is y square with respect to x? That is 0. So this x2 cancels off, leaving you with x divided by x square plus y square. Now I need uy. What is uy? In a similar fashion, log on differentiation is 1 divided by x square plus y square. And this x square on differentiation with respect to y gives me 0. And this y square on differentiation gives you 2y. So this 2 can be cancelled off, leaving us with y divided by x square plus y square. So my first step, namely computing ux and uy from the given u, is done. Let us now move on to our step 2. In my step 2, I assume ux to be phi 1 of z comma 0 and uy to be phi 2 of z comma 0. What we have computed in our step 1 as ux and uy, x by x square plus y square and y by x square plus y square. We notice that both of them are going to be functions of x and y. But now what we require is going to be function of z comma 0, which means what I will have to do is wherever I have x, replace it with z, and wherever I have y, replace it with 0. X, y, z, 0. So this is my working rule. So now moving on, this phi 1 of z comma 0 is nothing but z, x is replaced as z divided by x square. So z square plus y square, which is 0 square. So I have z by z square. So this can be written as 1 by z. So my phi 1 of z comma 0 is 1 by z. Now I need phi 2 of z comma 0. What is phi 2 of z comma 0? Uy with x and y replaced as z and 0. Replace x as y z, y as 0. So what will happen over here? Y will be replaced with 0. So what will happen to my phi 2? My phi 2 will become 0. So now I have my phi 1 and phi 2 ready with me for application. Step 3. Compute your f dash of z by substituting phi 1 of z comma 0 plus I phi 2 of z comma 0. I'm sorry, the sign over here is plus. So compute f dash of z as phi 1 of z comma 0 minus I times phi 2 of z comma 0. You can remember in this way that whenever we are having u and we are computing your f dash of z, it is going to be negative sign in between. And whenever we are having v and we are going to compute our f dash of z, then the sign in the center is going to be positive. For u, it is negative. For v, it is going to be positive. So now I know from my previous step that my phi 1 is 1 by z and my phi 2 is going to be 0. So on this substitution, I have f dash of z to be equal to 1 by z minus I times of 0. So now my step 4, which is nothing but, what is going to be step 4? Integral of my f dash of z will give me my f of z. So I am going to integrate my 1 by z with respect to dz. This part is already 0, so it is not going to affect me. What is 1 by z dz on integration? We have it to be equal to log z. Therefore, the required analytic function is going to be f of z is equal to log z. And it is obviously clear that log z has the real part as u is equal to half log x square plus y square. Now, let us move to the second problem where we have our v given. So, problem number 2, if the imaginary part v is equal to 3x square y minus y cube is given to me, then construct the analytic function f of z out of this. So what is my step 1? My step 1 is computing the derivatives of vx and vy. But in v, I need to keep in mind it is the opposite way round. That is, first we compute vy and then we compute vx. What is your vy? Vy will be equal to 3x square minus 3y square. What is your Vx? Vx is going to be 6xy minus 0. So my step 1 is over. What is going to be my step 2? Step 2 is the assumption Vx with respect, Vy, which is the function of x comma y, has to be rewritten as phi 1 of z comma 0. So x has to be replaced with that of z, y with respect to 0. Okay. So when I replace my x with respect to z and y with respect to 0, what is happening to my Vy? This Vy will now turn out as phi 1 of z comma 0. So what is my phi 1 of z comma 0? This will become 3z square and y is replaced as 0. So this will become minus 0. What is going to be the next assumption? I am assuming Vx, which is a function of x comma y, as phi 2 of z comma 0. So how is my Vx turning as? It is phi 2 of z comma 0. Again replace x with z, y with 0. When I replace x with z and y with 0, I have it as 6 z 0. So this will totally vanish. So my phi 1 equal to 3z square and my phi 2 is equal to 0. My step 2 is over. What is going to be my step 3? My step 3 is going to be computing my f dash of z. What is my f dash of z? It is phi 1 of z comma 0. We need to keep in mind v is given me center value is positive. I times of phi 2 of z comma 0. So this will now become, what is my phi 1? I have it as 3z square. So this is going to be 3z square and I times, what is my phi 2? This is going to be 0. So my f dash of z is 3z square plus I0. So this imaginary part will automatically vanish. And now moving on to my step 4. What is my step 4? From my derivative f dash of z, find your f of z. How to obtain it? Integral your f dash of z with respect to dz. So it is integral 3z square dz. So 3 z square on integration gives me z cube divided by 3. So this cancels off, leaving you with z cube. Therefore, my required f of z is z cube. So the analytic function which has this v, which is 3x square y minus y cube, as its imaginary part is nothing but f of z is equal to z cube. Hence, using a real part, we have constructed an analytic function, and in a similar fashion, using the imaginary part, we have constructed an analytic function. And what is the method which we have applied? We have applied Milne Thomson method. Just keep in mind the 4 steps which is required for your computation. The u will carry a negative sign over here. The v will carry a positive sign over here. Keep this in mind. And when it comes to ux and uy are evaluated in order for your phi 1 and phi 2. But when it comes to v with respect to y comes first and v with respect to x comes first. If you keep these 2 tips in mind, then Milne Thomson method can be easily applied to evaluate or construct the analytic function. Thank you.